Optics is the discipline that lies at the intersection of quantum mechanics and electromagnetic theory. The quantum theory of light was developed in the 1930s and 1940s, but is way too cumbersome to use to describe optical imaging systems. Whereas we saw last time, a single pixel may involve more than 1 trillion modes, and if we include the system as a whole, we could be dealing with systems where we have 1,000,000 or 1,000,000,000 spatial modes and 1 trillion temporal modes, so way over 10 to the 20th modes overall. Just way too cumbersome to think about this in terms of individual modes, so we need a more statistical theory to describe the state of these systems, and that theory was developed in the 1950s with the development of optical coherence theory. Emil Wolf, pictured here, was one of the pioneers of optical coherence theory, and in this seminal 1954 paper derived the Wolf equations, which describe the wave equation for the coherence functions of the field. So these equations allow us to propagate fields described by coherence functions. In chapter 4, we discussed how to describe geometrical systems and rays that propagate through systems. In chapter 5, we talked about how waves propagate and how we can propagate from a boundary condition of waves on one boundary to the boundary on the next boundary. And today we're going to talk about how to propagate coherence functions from one boundary to another. Computational imaging. Episode 42, Coherence Propagation. Here's a slide from way back in episode 27, where we were dealing with the problem of how to propagate the electromagnetic field from an input plane to a diffracted plane. So we had the field on this plane, and then we used the Maxwell equations to describe how the field propagates from the input plane to the output plane, and we found that the transfer function for free space is a phase delay, and so we could use the angular spectrum method to describe this diffraction. Today we generalize this problem to look at this situation where we know the cross-spectral density, W of x1, y1, x2, y2, on an input plane, and we want to find the cross-spectral density on the output plane. So this is a 4-dimensional function on each plane, or 5-dimension if we include the wavelength as well. So how do we solve for this problem? Well, it turns out to be extremely straightforward. We know how to solve the coherent problem, that we have the field distribution on the input plane. We can use the coherent impulse response, which would be simply the phase delay or the Fresnel kernel for free space propagation, and we can operate with that impulse response to get the field distribution on the output plane. Now, we can take the product of the field at point x1, y1 and point x2, y2 and multiply them together. And now we could write this double integral over the input fields as a quadruple integral over the input field from two different points. And now if we take the expectation value of this product, this expectation value is going to be the cross-spectral density on the input plane, and this expectation value is going to reduce to the cross-spectral density on the output plane. So we find we can describe coherence propagation by operating on the cross-spectral density on the input plane with the product of the coherent impulse responses at x1 and x2 on the input plane to transform to the x1 prime, y1 prime distribution on the output plane. So the impulse response for propagation of the coherence function is just the product in these different variables, x1, x1 prime, x2, x2 prime, of the coherent impulse response. So H sub c here is the impulse response for the coherent field. X1 prime is the spatial distribution on the output plane. X1 is the spatial distribution on the input plane. So this would be the kernel we would use to propagate the coherent field, and now we can propagate the coherence function by simply the product of the coherent impulse responses. Very straightforward, very simple. Of course, in very dynamic, complex situations, you would want to use the Wolf equations and differential calculus. But here, for imaging systems, typically we'll be able to use just plane-to-plane transformations using these impulse responses. Now, we will often be interested in fields which we'll call spatially incoherent. By spatially incoherent, we mean that the cross-spectral density on the input plane is delta correlated. that if we take the field from two different points, x1 and x2, we only see interference if those 2 points are identically the same. This is an approximation. Real fields are always going to be correlated, at least on something like the wavelength scale, but this approximation is very accurate for many situations where we have diffuse reflections or incoherent fluorescent sources or thermal sources. So we assume that the field is delta correlated on the input plane. Now, the important thing to understand about coherence is that the field is no longer delta correlated after it propagates. So fields gain coherence on propagation. So the cross-spectral density on this output plane, the x1 prime, y1 prime plane, is going to be this transformation of the incoherent emittance on the input plane. So S here would be the spectral emittance on the plane as a function of x and y. And now, because it's delta correlated, our four-dimensional integral transformation of the input cross-spectral density turns into a two-dimensional integral operated on by this product of the coherent impulse responses. Very, very straightforward. Let's look at the case of free space diffraction, where we assume that we can use the transfer function that we've seen previously for free space simple phase delay as a function of frequency. We can approximate this transformation using the Fresnel approximation so that our impulse response is the Fresnel kernel. And now if we operate on an incoherent source distribution, S of xy, with the Fresnel kernel, we have the product of the Fresnel kernel at x1 prime and the Fresnel kernel at x2 prime on the output planes. Those products simplify where the x squared terms will cancel, and so we get a kernel inside of the integral that is only a function of x, the input variable on the input plane, times delta x, where delta x is the separation of x1 and x prime, x1 prime and x2 prime. So the x1 prime squared and x2 prime squared terms we've combined into this function e to the I 2 pi nu q, where q is a function of delta x and x bar. So this x bar is the mean position of x1 prime and x2 prime, the positions on the output plane. But so this x bar times delta x, that's basically x1 prime squared minus x2 prime squared. But we find it more convenient to express w as a function of delta x and delta y and q. And so we find that if we can ignore this q term, which eventually we'll deal with the q term if z becomes large, w becomes stationary. The cross-spectral density is stationary on the diffracted plane. This transformation, describing the relationship between a incoherent source distribution and the remote cross-spectral density, is called the Cittert-Zernike Theorem. And what it tells us is that the remote cross-spectral density is the Fourier transform in terms of delta x over lambda z, the distance to the propagation of the input power spectral density, or the input field, the input incoherent field on the object. So we simply take the Fourier transform of the input source distribution, and that tells us our remote cross spectral density. An amazing and very powerful result. So let's look at an example of what this means really. So we have a remote source that's of diameter a, and it has a uniform spectrum, so uniform emittance everywhere within this circle of radius or diameter a, and then zero outside of that, and it's incoherent so that there's no interference in the plane of the source between 2 points if the points are not identically equal to each other. But after propagation, the cross-spectral density has this form. It's going to be the original spectrum times the Fourier transform of this circ, which of course is jinc of a times u, but here we're going to evaluate that at u is equal to delta x over lambda z, where of course lambda is c over nu. This nu and c is a 1 over lambda. We're going to define this delta theta to be a over z. That's the angular extent of the source observed from a distance z away, and of course by this u equal delta x we mean the radial coordinate square root of delta x squared plus delta y squared. So this JINK, if we plot it out, would look like this kind of standard JINK form with the width of 2.44 in units of this AU. But that AU is A delta X over lambda Z. So if we think of this in units of delta X, those units are going to be in terms of lambda Z over A, or lambda over delta theta. So the basic extent of this is going to be 2.4 times lambda over delta theta. If we think, for example, of the source being the sun subtends about 10 milliradians. This 0.0087 radians is the angular extent of the sun. And so the range over which we would be able to see interference, over which if we take 2 points and see some interference, which is what W describes. That says we take a point at x1 and x2 and look about how strong those 2 points can interfere. That's what the cross-spectral density describes, and the range over which we would see that, which we call the coherence cross-section, is going to be around 2.44 times lambda over delta theta, which is about 100 wavelengths. So we would expect to see coherence in sunlight on the range of around a couple hundred wavelengths, or maybe 100 microns of extent in the visible regime. So it's not big, but it's also not zero. So what we have on the surface of the sun is presumably an incoherent source, but the sun observed on Earth is partially coherent. If we have small sources, like let's say an LED source that illuminates a scene, those sources gain coherence on propagation, even though the source could be thermal and illuminate with incoherent thermal light. By the time it propagates some distance, it can gain substantial coherence, and the amount of coherence cross-section it's going to have is going to be inversely proportional to the cross-sectional angle subtended by the source. So incoherent sources gain coherence on propagation. You can see this in sunlight. Here's a seminal paper from 1975 looking at situations in which one can see partially coherent effects from the scatter of sunlight. And this is a particular surface. If you have a relatively smooth specular reflector, but look at it closely in sunlight, you'll see speckle effects, which is these interferometric effects in sunlight, which is a key feature of what we're talking about in this course, is that we need to model optical systems very carefully because very subtle effects occur. We saw that in chapter 6 when we saw that by carefully considering these quadratic phase terms, we can recover wavefronts in coherent fields. And now with incoherent sources, we'll still see partial coherence and coherence effects that we'll need to describe and understand to really build computational imaging systems. You can see this yourself. Here's a picture that I took this week of my fingernail. I laid my fingernail on my knee with sunlight streaming in through the window, and if you zoom in closely, you'll see speckle. So we're not going to get into a lot of detail to describe this speckle in this course, but we are going to consider very carefully how coherence propagates, how coherence is manifest in computational imaging systems, and we'll begin that discussion with our next episode when we talk about how to measure coherence in the most direct way with two-beam interferometers.